Let's talk about normal subgroups. The right context to introduce normal subgroups is from the notion of a group homomorphism. So let phi from one group G to another group H be a group homomorphism. So that means that phi is just a function from G to H which takes the multiplication operation of G to the multiplication operation of H. That is, phi of G1 G2 is phi of G1 into phi of G2. Now I define the kernel of phi, which I denote ker phi. It's called the kernel of phi, to be those elements k in G such that phi of k is the identity element of H. It's easy to see that kernel phi is a subgroup of G. Also, we define image of phi, which I'll call im phi, to be the set of all phi of G as G runs over G. In set theory, this is sometimes called the range of the function phi. This is a subgroup of H. Okay, just because phi is a homomorphism, these things have to be subgroups. Okay, now let's try to understand what are the elements which are the pre-images of elements of H. So take an element H in image of phi. So what does that mean? So there exists G in G, let's say G0 in G, such that phi of G0 is equal to H. Now question is, what are the elements that map to H? So claim set of elements G in G such that phi of G is equal to H is equal to G0 times kernel phi, the left coset of the subgroup kernel phi corresponding to G0, and it's also equal to kernel phi times G0, the right coset of kernel phi corresponding to G0. The proof is quite easy. So if phi G is equal to H, then phi of G0 inverse G is phi G0 inverse phi G by the properties of homomorphisms, but phi G0 inverse is H, so this is H inverse, and phi G is also H. This is the identity of H. Therefore G0 inverse G belongs to the kernel of phi, and hence G belongs to G0 times kernel of phi. I'm just multiplying both sides of this equation by G0. Okay, and you can do the same thing for kernel of phi times G0. For this inclusion, you just write it the other way, phi of G times G0 inverse. And to go the other way, suppose G is equal to G0 times K, where K belongs to kernel of phi. Then phi of G is phi of G0K, which is phi G0. What is phi of K? Well, phi of K is 1, identity of H. So that's just phi G0. So this is pretty straightforward. So what we see is that when you have a homomorphism, its kernel is a very special kind of subgroup. Its left cosets are also its right cosets. Okay, so writing K for the kernel of phi, what we just saw is that G0K is K G0 for all G0 in G. Okay, this argument that we had earlier applies to any element of G. This can be rewritten as G0K multiplying both sides by G0 inverse is equal to K. This basically defines a normal subgroup. A subgroup H of G is said to be normal if G inverse is equal to H for all G in G. Okay, so we've seen that the kernel of a homomorphism is always a normal subgroup. For any homomorphism phi G to H, kernel phi is a normal subgroup. Of G. Let's look at a somewhat more specific example. So last time in one of the earlier lectures we saw that the symmetric group Sn goes into, there's a homomorphism from the symmetric group Sn into the matrix group GLN of invertible n by n matrices with, say, entries in the real numbers. So what was this thing? The permutation W goes to the matrix with columns EW1, EW2, EWN, where EWI is the ith coordinate column vector. And from GLNR to R star, so non-zero real numbers under multiplication, we have the homomorphism determinant. So if you compose this, so let's call this I, then determinant circle I is a homomorphism from Sn to R star, and the kernel of determinant circle I is what is called the alternating group An. This is the subgroup of the permutation group consisting of all permutations whose for which the corresponding permutation matrix has determinant +1. Okay, and because it's the kernel of a homomorphism, AN is a normal subgroup of Sn. Here's another question for you. So we have this in an earlier lecture we saw that Sn minus 1 sits inside as a subgroup of Sn. You just think of it as the subgroup of Sn consisting of all permutations which take n to n. The question is Sn minus 1 a normal subgroup of Sn? So you can try to think about this yourself.